So we're going to look at Brewster's law next, and I'm going to just draw the diagram so we can talk about the terminology for how we have our apparatus set up. We've got an incident beam of light, and in general it's polarized like this and also in and out of the page. So because this is what our apparatus looks like when viewed from the top down, I'm going to call these horizontal and the up and down coming in and out of the page vertical. We're incident on the surface here, and we have a reflected beam and a refracted beam. And we'll call these indices N1 and N2. For our apparatus, this is going to be air, and this is going to be glass. So when you have a mixed polarization beam incident on the surface or the interface here, what happens is some of the light is refracted and transmitted and some of it's reflected. And in general, the different polarizations are going to be affected differently. So it's just basically the way that it works out from doing the detailed electromagnetic interaction equations with boundary conditions and everything. What you get at the so-called Brewster's angle is this reflected beam. It's vertically polarized, or you may see it referred to as polarized in the plane of the interface, and that's because this air glass interface extends horizontally and vertically. And so the component that's not polarized vertically is all transmitted, and the reflected part is all vertical. So here's the apparatus that we're going to use. We have our laser projector, there's a horizontal polarizer, and a piece of glass mounted on a rotating platform with a protractor so we can read the angle that it's rotated through, and a projection screen in the back. So if I turn the laser on, we can look at the reflected beam back there as a function of the angle. So if I turn on the laser, I've just double checked that when I have the glass oriented so that the beam is reflected back at the laser, my pointer on the protractor is reading 0, and can rotate this around and kind of swing it across the screen. You may see a little bit of brightness variation, but it's hard to tell exactly what's going on. So what we can do is insert a polarizer. And so now what I'm doing is inserting a horizontal polarizer, which means that the vertical part is removed. And so now all of the light waves that are hitting have the E field oscillating in the horizontal plane. And now we can look at the intensity of the reflected spot as a function of the angle. And you can see it on the back, it's getting pretty dim back here. Maybe I'll turn the lights down so we can get a little better look at that variation. And it's starting to brighten again towards the back. Minimum around there, and then brighter again. So we removed the part that's vertical, and at Brewster's angle, only the vertical part is reflected. So I'll just run through that again, this time with the lights down so it's a little easier to see the minimum. So as I'm sweeping around, the brightness is going down, probably with our minimum somewhere around here, and then increasing again. So brighter to either side, and the minimum right around here. So I've got a horizontal polarizer in the path before the reflection, but if I take that out, then we get a nice big spot on the screen, and we have basically mixed polarization incident on the screen. But if we're near Brewster's angle, then it should be almost all vertically polarized after reflection. So you can see if I put in a vertical polarizer there, we still have our bright spot on the screen. But if I insert a horizontal polarizer, it's almost all blocked. So now with the lights on to measure the angle, looks like the reading on the protractor is pretty close to 305, which means the glass has been rotated through 55 degrees and the incident angle is 55.